सॉल्व कर दें। अच्छा, जो YouTube लेक्चर्स मैंने आपको अंडरग्रेड की बता दिए ना एम्बेडेड सिस्टम के, तो आप अगर यहाँ से लेक्चर 1 से लेकर लेक्चर अगर जितने आपने अगर कोई क्लास से कोई कंसेप्ट समझ नहीं आ रहा, अब मुझे ये नहीं पता कि कौन कौन सा टॉपिक मैंने कहाँ पे कराया है, ठीक है, लेकिन ये है कि वो ऑलरेडी जो टॉपिक्स है वो सीक्वेंस में ही है। तो अगर आपको मतलब लाल सेब भी ऑलरेडी यूट्यूब लेक्चर्स को कर रहे हैं, हो सकता है हम इसको भी अपलोड कर दें, ठीक है, हो जाएंगे आप जी जी सर। जो कंप्रेस हो जाएंगे तो मैं अपने यूट्यूब चैनल में इसको एडवांस कंप्यूटर आर्किटेक्चर, ठीक है, उसके साथ लेक्चर। तो अगर आपको इधर भी अगर आपने जल्दी करना होगा तो हम उसको भी इस तरह से वो कर सकते हैं, ठीक है। देखते हैं कौन कौन से पेन काम कर रहे हैं उसके बाद टेस्टर। Move again with the stack addressing mode, and now we will explain some of the details of the stack addressing mode. So why stack is necessary? Why stack is necessary? Anybody, do you have any idea? Because you are from the computer background, okay? Why stack is necessary? When you want to call a function, so actually you jump to a new subroutine, but when you have to return from a subroutine, then you need to save the address of the current program counter on the stack. So in this case, the value is pushed on the stack. The value is pushed on the stack. But when you have to return, now let's assume if you have a main function. Let's assume if you have a void main void. Let's assume you have a function, main function, and you are calling some function f1. You are calling some function f1. So when you call this function f1, where the control will be transferred? The control will be transferred to the first line or the first statement of this function f1. But when when function finishes, where the control should be transferred?
Then back to main.
The control is transferred back to the main control. So actually, when you want to call, you are calling a function, the control is transferred to this f1. So actually, now if you look at this function, so there maybe there is some instruction here. This is the last instruction before this calling this instruction. So actually, program counter was pointing to this instruction. Okay, program counter was pointing to this function. But when you are calling a function, so actually the program counter will be implemented. It will be now pointing to this function. And if you look at this function, so actually it is actually a jump instruction. So actually it is just like in assembly, it is just like this. Jump label. When it's a jump label, so actually the program counter is now updated. The program counter value is now updated, and it is actually starting to actually this function is stored in memory with some address f1 address, and now program counter is pointing to this location. But when you have to return from this subroutine, where the control should resume? After the next instruction that is followed by f1. So actually what you do, and at this point now this is the next instruction following f1. So now before having a jump to this instruction, the value of this address, this instruction address, is stored on the stack. So let's assume this address is 56320x563. So this is 0x5632. So it is pushed on the stack. When the subroutine is called, and when it's finished, so actually it will pop that value from the stack, and where the control is transferred. The control is transferred back to the main. So actually, if you are calling another function within this, let's assume f2. So actually, then you are jumping from this function to another function f2. So in this case, the address of the instruction that is following f2 is then pushed on the stack. When it will return, so first, then let's assume this instruction address is 0x9632. So then 0x9632 is pushed on the stack. Now when you execute the last instruction, okay, what is the assembly equivalent of this? Assembly equivalent of the last instruction, if you remember, RET, return. So actually return is actually a hint that whatever the program counter values be pushed on the stack, it will be retrieved back and the program counter will be updated. So actually, how the microprocessor executes the instruction? Typically, microprocessor executes the instruction in sequence. How the flow is changed?
Through loops or
through jump instruction. So there are different types of jump instruction: conditional jump instruction and unconditional jump instruction. If you are calling a function, so it is a conditional jump or unconditional jump? It is unconditional jump. It is an unconditional jump. So when an unconditional jump, so actually the address of the instruction following this jump instruction will push on the stack. And this when finishes, so it will be retrieved and the program counter will be updated. So now let's assume these are different instructions. First instruction is executed, then next instruction, then next instruction. Let's assume there is a jump. It will jump to the subroutine and this address is stored back. When it will return, so it will resume from that particular. Let's assume I am teaching in the class, okay, and I am asking the name of each student, individual student. Class, what's your name? What's your name? What's your name? And somebody raises, oh, please serve me. I will serve. And then I will return back from where I was interrupted. So this is the advantage of the stack. Okay. So now, if you consider the memory layout, let's say we have a memory. So now this is your memory. So memory stores some instructions. It also stores some data, and this is also some
stack
area that is dedicated for the stack. And actually, if you look at the stack operations, actually it is a last in first out data structure. So typically it moves from bottom to top. So now let's assume a scenario that we have 4 MB of cache, 4 MB of memory, and the program size is 4000 KB. So what is the stack size? So to maintain a stack, we need two things. One is the bottom address, another is the base address. And we also need another parameter, that is the stack pointer. So we need a bottom address, then we need a base address, and then we need a stack pointer. So stack pointer is actually pointing to the current location. So now for this memory, let's assume we have a 4 MB of memory. 4 MB of memory. So we can directly write it 2 is for 2, 2 is for 20, and 2 is for 3. Okay? It is 2 is for A cross W. What is A? Address lines. What is W? Data lines. So it is 2 MB. So 2 MB is to A cross W. So actually how it is actually, let's assume W is 8. So it is 2 is for 21 cross 8 is equal to 2 is for A cross 8. What is address lines? 21. What is the minimum address and what is the maximum address? What is the maximum address? What is the minimum address? The minimum address is 0x00000, and the last address is 0f1. Why 1? The minimum, this address is in hexadecimal. So if we convert it into binary, so actually it will be 21 bits. It will be 21 bits. When it will be 21 bits, how many zeros will be there? 21 zeros. And how many ones? 21. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1. So this is F, 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 and F. 1, 2, 3, 4, 5. Agreed? So this is the minimum memory address, and this one is the maximum memory address. Okay? Okay, so the minimum memory address, actually whenever operating system allocates some data for the program, so the memory stores some instructions, memory stores some data, and some space is dedicated for the stack. Okay, now we say the program size is 4000 KB. Program size is 4000. So if we say okay, it's 4 MB. Okay, sorry, not 20, it's 4 MB. 4 MB, so it's it is called 22 नहीं होगा?
ठीक है वो 25 होगा सर
22 होगा ना?
हाँ 22 होगा yes.
It will be 22. But if we say that W is 16, let's assume W is 16. If W is 16, so actually यहाँ A is equal to 21 होगा. A plus W इसको calculate कर ले, A will be 6. So it will be A1FFFE. Okay. So our memory size is 4 MB. So 4 MB, can we write it like this? 4 M K KB. K stand for kilo. So 1 megabyte is equal to KKB. So it is equal to 4096. So what is K? 4 multiplied by 1024 KB. So actually equal to 4096 KB. What is the program size?
4000.
What is the stack size now? So this is your program size. Program size, which is 4000 KB. And what is your stack size? 96 KB, kilobyte. So this is your stack size. Okay, now when we want to push some data into the stack, so you should not push the data to the stack when the stack is full. When the stack will be full? When stack will be full? When stack pointer is pointing to this, the first location. So actually, it is actually base. So the stack will be full when the stack pointer is pointing to the base address. And when stack will be empty,
And it's pointing to that.
when it is pointing to the bottom address that is lying. Okay, now we studied different addressing modes. We studied register indirect with pre-decrement. We studied register indirect with post-increment. Which addressing mode will be used for maintaining stack? Because stack is moving from bottom to top. Register indirect with pre-decrement or post-increment? We are moving from bottom to top. Pre-decrement. So to maintain a stack, so actually we will use register indirect with pre-decrement. So now how do we do this? Okay, now think it from the perspective of a processor. If you remember in our base architecture, how many address registers we had? How many address registers were there? There was some
32.
data register and some address registers. If you remember, there was some data register starting from R0 to R31, and there were some address registers starting from A0 to A15. So we assumed in our architecture there were 15. Let's assume in our architecture there were 15 address registers. So A0, A1, A2 up to A15. Okay. Now let's assume a scenario that now this A15 is an address register which is pointing to the stack. So actually, what is now A15? It is a stack pointer now. It is a stack pointer. Now what we have done, we have dedicated this A15 What is A15? A15 is an address register. When it is an address register, it is pointing to an address in memory. It is pointing to an address in memory. So how we can initialize this stack pointer? So we can initialize this stack pointer like this. Move A15 hash 0x dollar 0x f. So now we are pointing this A0x f. Actually it's 1. So it is actually pointing to this bottom. So now when we initialize this stack pointer, so this stack pointer should be initialized to the bottom address. Should be initialized to the bottom address, and it will move above. Okay. Which addressing mode is this?
Immediate.
Immediate. This one is immediate addressing mode. It is an immediate addressing mode. It means that the contents of this will be loaded into address register. So now address register A15 contains 0x1FFFE, and now it is pointing to this location. Okay. Which addressing mode is this? Register addressing mode. Because the destination is register. So now we have two types of register. One is an address register and one is a data register. Okay. Data register contains some data. Address register contains an address of memory. Agreed? Okay. Now we are performing some operations. How it is actually how the stack is maintained using assembly instruction. How we can maintain operation. Now if you say push R5, okay, push R6, pop R9, pop R10. Let's assume we have this code. Okay, so now push is actually we are inserting an element to the stack. So actually when you are pushing, so it is equal to move. So the memory will be source or destination? Destination. The memory is destination, which is pointed out by which address register? A15. So it is memory is your destination A15, and which addressing mode we will use? Minus. Because in push operation we are moving from bottom to top. Okay, so move minus A15 and R5. So actually this instruction is actually a logical instruction. We are pushing some element on the stack. But what will be the actual code? So which addressing mode will be used? Register indirect with pre-decrement. So first address register will be decremented. So actually now let's assume if the size of this data, we say the size of this data is 2 byte or 16 bits. The size of the data is 2 byte or 16 bit. So actually if you say this address contains this data 5A32, I am writing every data in hexadecimal. Okay. What will be the next address? 0x000002. One is even address and odd address. We assume that the memory is byte addressable. Okay, that's the reason that we are using a decrement of 2. That's the reason that the last address is 1FFFE, not 1FFFF. Okay. Now A15 is pointing to the bottom address. First is decremented. So what's the new value? So at this point, after this instruction, first A15 will be decremented. What will be the value of A15? So now A15 has the value of 1FFFE. First it will be decremented. So what will be the new value? 1FFFFC. So actually this address will be FFFC. So 15. So first the value will be pushed. Which value will be pushed? R5. Let's assume we have some register R5 and its contents is 9321. So this value will be pushed on the stack and address register will be pointing to this location, and the value that is moved on the stack is now 9321. Okay, now again push R6, move minus A15, R6. Let's assume that the contents of R6 is 663A. So now the address register will be updated. Now the new contents will be 1FFFA, and it is now pointing to the next location, and the new value, that is 663A. Okay, now we are popping. So if you want to remove some elements, so the memory source or destination? Memory source. We are copying the element from the stack. We are copying the element of the stack, so it means that now this value will be moved into register R9. So now let's assume we have some register R9 and that value has 0, 0, 0, 0. So who is pointing to the stack? A15. What is the new value? 1FFFA. It is now pointing to the stack. This value will be moved to register R9. Okay, so now how we can write it like this? Move, it's actually move. R9 register is now the destination. Register is now the destination, and what is the source? A15 plus. So because we are using register indirect with post increment. First the memory value is accessed. The memory is accessed. So now in this case, new value, first the memory is accessed. This value will move into register R9. What are the value of R9 now? 663A. This 663A will be moved, and actually again the new value will be 1FFC. Now the stack pointer will point to the 63. Okay, now if we say pop R6, so move R9, move pop R10, sorry, move R10. So let's assume that the initial value of R10 is 1132. So move R10 A15 plus. So actually now the stack pointer is pointing to this location. This value will move into the register R10. What is now the new value? 9321, and it will again point to this location. So now we have two things. So actually, if you want to again pop some element from the stack, now the stack is empty. So actually, before performing a push or a pop operation, first you should compare the content of the address register A15. So if A15 is equal to the bottom address, it implies that the stack is empty. So you need a check. First you need a check. So if you want to have a fail-safe program, first you need to check where the stack is empty. If the stack pointer is pointing to the bottom address, what does it imply?
It's an empty
Stack is empty. If the stack pointer is pointing to the base address,
stack is
हमें तो चेक इस बात पे चाहिए कि stack pointer is addressing to the base address or not.
No, we can have some kind of a comparator. If it is within the range of the base and the bottom address, and actually there are two methods. One method is using the software, and one method is using the hardware. In the software, you need an additional. So actually, if we say, so in software, how you can implement it? If the contents, I'm just writing in C++ just for the sake. If A15, what is A15? A15 is actually the content of the stack pointer. If A15 is equal to bottom address, what does it imply? Stack is empty. Else if A15 is greater or equal to, greater than base address, smaller than base address? Smaller than.
No,
equal to. Greater than. Let's do the base address. You have jumped into switch. So greater or equal to base address, then stack is full. Else you are allowed to perform a push and pop operation. Okay, now this is one implementation. Now this is the software implementation. But in this software implementation has one drawback. This software implementation is one part. Before performing each push and pop operation, you need to check the content of the address register each time. Is it efficient or inefficient? Inefficient. How can you do it efficiently? Now this is a question. Why I'm telling you all these things? That we are complaining now hardware implementation. What can we do now? What can we do? Ji.
काउंटर होना चाहिए उधर अगर
कैसे counter enable? I don't want to write extra instruction, because if I'm writing this instruction before each, let's say before this push instruction, what check we need to make?
whether the stack is empty or full.
No, for push we need to check
If the stack
if stack is full. For push we need to check whether the stack is full, but for pop
we need to check stack is empty.
we need to check. So this check is performed when we want to pop. This check is performed we want to push. How we can avoid this problem? Now that's the reason that we want to compare different designs. How we can do this?
So we can make a flag counter or any
Where
variable.
how counter कैसे variable?
फ्लैग वेरिएबल एक मतलब उसको एक वैल्यू असाइन कर देंगे, उसके बाद अगर वो बार-बार चेक नहीं होगा, एक बार चेक होके तो वो नेक्स्ट वाली जो है ना इंस्ट्रक्शन पुश के लिए वो एक इंस्ट्रक्शन परफॉर्म होगा।
हर इंफॉर्मेशन यहाँ पे अवेलेबल है, इंफॉर्मेशन इज अवेलेबल यहाँ पे।
when the stack is full, further execution should be interrupted, so we need to generate
No. It's a very simple thing. Every information is here. I will explain this, but I need some info from your side. How we can do this? If you want to perform any push or pop, so we need to define 3 registers. We need to define 3 registers. First register is SP. What is SP? Stack pointer. Actually, it will move upward or downward. And then we need another register, base, and then bottom, base, and we initialize this base and bottom beforehand. So we initialize base. Let's assume this address. Not for this particular example. Let's assume this value is 0FFF0. Let's assume this value is this 0FF000. Let's assume this is value is this. So actually, what we need. So actually, if we say that if it's 0FF000 and the bottom is 1FFFE, and now we need a hardware check will be made internally. A hardware check will be made internally, and it will compare the contents of the stack pointer with these 2 addresses. If the contents of this stack pointer is within this range, so it's a valid address. And if this is outside this range, so what do we need? We need some internal comparators.
सर ये सिस्टम स्पेसिफिक नहीं होता
क्या कह रहे हैं?
ये सिस्टम स्पेसिफिक
Yes, system specific. Yes. So in actually if you want to perform push and pop operation, and if the architecture support this, so actually you are reducing the code size. Why? Because if you are pushing each instruction, you need 1 instruction. And let's assume if you want to perform 1000 push operations, so you need 1000 instructions unless it is in a loop. So you are increasing the code size. To avoid increasing the code size, what we can say that whenever the stack pointer value does not lie within this range, the system by itself will generate and interact that the stack is overflow, or the stack is empty, or the stack is full. So this is actually what you can do. It's done by the system automatically, and it should not lie within the range. And actually, it's not only from the perspective of the stack, it's also from the perspective of programs. I will explain it why. Let's assume we are running different programs. And what operating system does? Operating system assigns some space for each programs. So conceptually, what we said that a program consists of instruction and data. Let's assume if there are multiple programs. Multiple programs can be a Word file, can be an Excel file. So okay, let's assume we have multiple programs. This is program P1, P2, P3 and P4. Let's assume here are 4 programs that are currently running. It can be Word file, it can be Excel file, it can be any kind of. Now let's assume if base address is A and base address is B, if base address is C, base address is D, E and F and G and H. What is A?
0.
No. A is actually the base address of program B1. Yes, if you say okay, what is B?
Base address of program.
The bottom address. The bottom address of program B1. The base address for program C. Okay, now let's assume that if you are playing with the pointers, let's assume the pointers and pointers access some memory, and if you have written a bad program, and you are pointing to an address in memory that belongs to another program, let's assume this program P1 generate an address. This program generate an address. This program should generate an address that lies within address range of this program P1. It should not generate an address that it should not access the address space of another program. And if it accesses the address space of another program, it will be a great chaos. It will be a chaos for the operating system. So actually, what's the job of the operating system? The job of the operating system is to perform the isolation between different programs. It allocates space to different programs, and it also takes care that one program should not generate an address that lies within